Good morning. This lecture addresses propositional logic. We discuss several definitions and give examples of their applications. We conclude with several exercises from our text that are similar to those that are assigned. Definition 0. A proposition is a declarative sentence that is either true or false, but not both. Example 1.1. The following is a declarative sentence. Washington, D.C. is the capital of the United States of America. True. Example 1.2. The following is a declarative sentence. Toronto is the capital of Canada. False. Example 1.3. The following is a declarative sentence. 1 plus 1 equals 2. True. Example 1.4. The following is a declarative sentence. 2 plus 2 equals 3. False. Example 2.1. The following is not a declarative sentence because the sentence is not a statement of fact. The sentence is a question. What time is it? Example 2.2. The following is not a declarative sentence because the sentence is not a statement of fact. The sentence is a command. Read this carefully. Example 2.3. The following is not a declarative sentence because the sentence cannot be shown to be either true or false. X plus 1 is equal to 2. Example 2.4. The following is not a declarative sentence because the sentence cannot be shown to be either true or false. X plus y is equal to z. Definition 1. Let P be a proposition. The negation of P, denoted by not P, also by overbar P, is the statement, it is not the case that P. The proposition not P is read not P. The truth value of the negation of P, not P, is the opposite of the truth value of P. Example 3. Find the negation of the proposition Michael's PC runs Linux and express it in simple English. Solution. The negation is, it is not the case that Michael's PC runs Linux. The negation can be more simply expressed by Michael's PC does not run Linux. Example 3.1. Find the negation of the proposition today is Friday and express this in simple English. Solution. The negation is, it is not the case that today is Friday. The negation can be more simply expressed by today is not Friday. Example 4. Find the negation of the proposition Vandana's smartphone has at least 32 gigabytes of memory and express this in simple English. Solution. The negation is, it is not the case that Vandana's smartphone has at least 32 gigabytes of memory. This negation can also be expressed by Vandana's smartphone does not have at least 32 gigabytes of memory, or even more simply as Vandana's smartphone has less than 32 gigabytes of memory. Example 4.1. Find the negation of the proposition at least 10 inches of rain fell today in Miami and express it in simple English. The negation is, it is not the case that at least 10 inches of rain fell today in Miami. This negation can be expressed more simply by less than 10 inches of rain fell today in Miami. Table 1 displays the truth table for the negation of proposition P. This table has a row for each of the two possible truth values of a proposition. Each row shows the truth value of not P corresponding to the truth value of P for the row. If P is true, then not P is false. If P is false, then not P is true. Remark. The negation of a proposition can also be considered the result of the operation of the negation operator on a proposition. The negation operator constructs a new proposition from a single existing proposition. We will now introduce the logical operators that are used to form new propositions from two or more existing propositions. The logical operators are also called connectives. Definition 2. Let P and Q be propositions. The conjunction of P and Q, denoted P and Q, is the proposition P and Q. The conjunction P and Q is true when both P and Q are true and false otherwise. Table 2 shows the truth value for the conjunction of two propositions. When P and Q are true, then the the conjunction P and Q is true. Otherwise, it is false. Example 5. Find the conjunction of the propositions P and Q, where P is the proposition, today is Friday, and Q is the proposition, it is raining today. Solution. The conjunction of these propositions P and Q is the proposition, today is Friday and it is raining today. The proposition is true on rainy Fridays and false on any day that is not Friday and on Fridays when it does not rain. Definition 3. Let P and Q be propositions. The disjunction of P and Q, denoted P or Q, is the proposition P or Q. The disjunction P or Q is false when both P and Q are false and true otherwise. Table 3 shows the truth table for the disjunction of two propositions. When P and Q both are false, then P or Q is false. Otherwise, it is true. Example 6. Find the disjunction of the propositions P and Q, where P is the proposition today is Friday and Q is the proposition it is raining today. Solution. The disjunction of these propositions P or Q is the proposition today is Friday or it is raining today. This proposition is true on any day that is either Friday or a rainy day, including rainy Fridays. It is only false on days that are not Fridays when it also does not rain. Definition 4. Let P and Q be proposition. The exclusive OR of P and Q, denoted by P exclusive OR Q, is the proposition that is true when exactly one of P and Q is true and false otherwise. Table 4 shows the truth value of the exclusive OR of two propositions. P exclusive OR Q is false when P and Q have the same value. That is, when P and Q are both true or when P and Q are both false. P exclusive OR Q is true when P and Q have different values. That is, when P has a value of true and Q has a value of false, or when P has a value of false and Q has a value of true. Conditional statements. Definition 5. Let P and Q be propositions. The conditional statement, P implies Q, is the proposition if P, then Q. The conditional statement, P implies Q, is false when P is true and Q is false and true otherwise. The conditional statement, P implies Q, is called the hypothesis or antecedent or premise, and Q is called the conclusion or consequence. Table 5 shows the truth value for the conditional statement of two propositions. When P is false, P implies Q is always true. When P is true, then P implies Q has the same value as Q. The statement P implies Q is called the conditional statement because P implies Q asserts that Q is true on the condition that P holds. A conditional statement is also called an implication. Here are some alternative phrases for P implies Q in Figure 1. If P, then Q. If P, Q. P is sufficient for Q. Q if P. Q when P. A necessary condition for P is Q. Q unless not P. P implies Q. P only if Q. A sufficient condition for Q is P. P, Q whenever P. Q is necessary for P. Q follows from P. We will need these phrases in our exercises later, and we have to note very carefully where the Q is and where the P is to be able to find out P implies Q. Example 7. Let P be the statement Maria learns discrete mathematics, and Q the statement Maria will find a good job. Express the statement P implies Q as a statement in English. Solution. From the definition of conditional statement, we see that when P is the statement Maria learns discrete mathematics and Q is the statement Maria will find a good job, P implies Q represents the statement if Maria learns discrete mathematics, then she will find a good job. Alternatively, we can say Maria will find a good job when she learns discrete mathematics. Or for Maria to get a job, it is sufficient for her to learn discrete mathematics. Notice here that the conclusion is stated first and the condition is stated second, but it's still P implies Q. Maria will find a good job unless she does not learn discrete mathematics. What is the value of variable x after the statement if 2 plus 2 equal 4, then x is assigned x plus 1? If x equals 0 before the statement is encountered, the symbol colon equals stands for assignment. The statement x is assigned x plus 1 means the assignment of the value x plus 1 to x. Solution. Because 2 plus 2 is equal to 4 is true, the assignment statement x is assigned x plus 1 is executed. Hence, x has the value 0 plus 1 equal 1 after this statement is encountered. Converse, contrapositive, and inverse. We have discussed implication, P implies Q if P then Q. The converse of P implies Q is Q implies Q if Q then P. The contrapositive, P implies Q, is not Q, implies not P. If not P, then not Q. The inverse, P implies Q, is not P, implies not Q. If not P, then not Q. Only the contrapositive, not P, not Q implies not P, has the same truth values as the implication P implies Q. When two compound propositions have the same truth values, they are called equivalent. Equivalence is noted by the triple equals operator. What are the contrapositive, the converse, and inverse of the conditional statement? The home team wins whenever it is raining. Solution. Because Q whenever P is one of the ways to express the conditional statement P implies Q, the original can be rewritten as if it is raining, then the home team wins. The contrapositive is not Q implies not P. If the home team does not win, then it is not raining. The converse, Q implies P. If the home team wins, then it is raining. The inverse, not P implies not Q. If it is not raining, then the home team does not win. Note, only the contrapositive is equivalent to the original statement. Definition 6. Let P and Q be propositions. The biconditional statement, P if and only if Q, is the proposition P if and only if Q. The biconditional statement, P if and only if Q, is true when P and Q have the same truth value and false otherwise. Biconditional statements are also called bi-implications. In Table 6, we see the truth values of the biconditional operator, P if and only if Q. And you can see from the table that when P and Q have the same value, then P if and only if Q is true. When they have different values, then P if and only if Q is false. It's worth noting that P if and only if Q is the complement of P exclusive OR Q. The truth value for P if and only if Q is shown in Table 6. Notice that the statement P if and only if Q is true when both the conditional statements P implies Q and Q implies P are true and is false otherwise. That is why we use the words if and only if to express the logical connective and why it is symbolically written by combining the symbols right arrow and left arrow. There are other common ways to express P if and only if Q. P is necessary and sufficient for Q. If P, then Q, and conversely, P IFF Q. The last way of expressing the biconditional statement, P if and only if Q, uses the abbreviation IFF for if and only if. Notice that P